This lecture is on heap sort, and their time complexity analysis. Here's a roadmap of what we will cover. In this video, we will cover the last basic operations of heaps, which is the delete method. Of course, we will also go over its time complexity analysis, especially the average case analysis. For simplicity, we will only deal with max heaps in this video. Let's get started. So what purpose does the delete method serve? Well, the delete method doesn't delete a target node in a given heap. It only deletes the root node. In the end, it will return the value of the deleted root node. When you delete the root node, you no longer have a heap anymore, so you need to take some extra steps to restore its heap property. As such, the delete method involves a few steps. First, you will start by replacing the value of the root node with the value of the last node at the last level. As you do that, of course, you need to store the value of the root node somewhere else so that you can return it eventually when the heap property is restored. Second, you will delete the last node. I mean the one that you just used to replace the value of the root node. Third, you will perform a process known as heapify to restore the heap property. You will start this process with a new root node and keep comparing it with its largest child. If the parent is smaller than that child, you will swap the two nodes. You will keep doing this sort of comparison iteratively until the heap property is fully restored. In the end, you will return the value of the original root. Step 3 is the process that we know as heapify. The reason why it's worth mentioning is that it's not only being used here in the delete method, it's also used in heap sort as well. Let's try to apply these 4 steps to the example max heap sitting on the left side. Our goal is to delete the root node, but instead of plugging it out of the heap, we would approach this by replacing the value of the root node with that of the last node. By saying the last node, I'm referring to the node sitting at the very right side at the last level. And I'm counting the levels starting from the root. So in our case, the last node has a value of 5 and sits at the index of 6. When you use its value to replace that of the root node, you will end up with this. Of course, you still need to store the value of the original root somewhere else because you need to return it in the end. After that, you will delete the last node, as it has served its purpose and no longer useful to us anymore. Keeping it will only create redundancy we don't want or need. So deleting the last node, we will have this. So far, we went over step 1 and 2. As you can see from this example, the root node contains a value of 5 now, which is smaller than its children. So we need to take the step 3, the heapify process, to restore the heap's property. The current root has a value of 5, and it has 2 children, with values as 7 and 10. Both are larger than 5. 10 is the largest child, so we will swap 5 with 10, like this. After that, you will continue to focus your attention on the node of 5 and see if it is at the right place by comparing it to its largest child. So now the node of 5 has only one child, which is 4. 4 is smaller than 5, so 5 is at the right level, and we can stop here. In the end, you will return the value of the original root, which is 11. That's how the delete method works. To translate these steps to pseudocode, you will have a delete method. The delete method does a few things. The first 2 lines stores the value of the last node at the last level before removing it. The next 2 lines stores the value of the root before replacing its value with the last node's value. After that, it will call on the help from a method named heapify. In the end, it would return the value of the original root. We know that the heapify method corresponds to step 3, but what does that look like? The heapify method takes an integer as its only parameter, which is the index of the starting point of the heapify process. As you can see from the delete method, heapify 0 means that the starting point of this heapify process should be index 0, or say the root of the heap. Underneath the while loop of the heapify method, it would compare the value of the parent node with its largest child. The parent may have 2 children or only 1 child, and that's the job of another helper method to figure out. This method is called maxChild, which returns the index of the largest child. If the parent node is smaller, it will swap their values and update the index I to the index of its maxChild. If the parent and the largest child are in the right order, it will break out of the while loop. To make sure we are on the same page, the pseudocode of the maxChild method looks like this. It takes a single parameter representing the index of the parent node. Underneath this method, it computes the index of its left and right child, makes sure that both would exist, then compares the two, and returns the index of the largest child. Just in case you think the logic of the maxChild method is odd, it has an if and else statements. For the if statement, the condition has 2 parts. The first part is when the right child doesn't exist. The second part is the left child is bigger than the right child. In both of those cases, it will return the index of the left child. Okay? Otherwise, it would return the index of the right child. That's the logic of the maxChild method. It's not hard to see that the maxChild method runs on constant time, because it only contains an if-else condition. The same thing can be said for the first few lines of the delete method as well. It takes constant time to run them too. The only thing that's worth our attention when it comes to the time complexity analysis is the heapify method. How much time does that take? To be succinct, we will hide the delete method and the maxChild method so that we can focus our attention on the heapify method. The time complexity of the delete method is in proportion to that of heapify process. As soon as we figure out the time complexity of the heapify method, the time complexity of the delete method will be self-telling. So what's the time complexity of the heapify method? In the best case, things are quite trivial. When you have a max heap composed of a single node, deleting it takes constant time, and the heapify method doesn't run at all, so that's constant time, expressed as T of n belongs to big O of 1. What about the worst case? The worst case must be when you have to perform swapping level by level from the root all the way to the leaf. For example, we have a max heap like this. When we follow the process of the delete method, we will replace the node 11 with node 3, and remove the last node afterward. Like this. After that, we need to rely on the help from the heapify method to restore the heap property. We will swap node 3 with its largest child, node 10, like this. After that, we need to continue this process by swapping node 3 with its largest child, node 5, like this. That's an example of the worst case. In other words, the heapify method needs to perform as many swapping as the height of the heap. What's the relationship between the number of nodes and the height of a heap? It's exactly the same as we studied for the insert method. If a heap contains n nodes in total, the height of that heap will be log n. That said, the heapify method involves log n number of swapping. Each swapping takes constant number of steps to run. so that the time complexity of the delete method under the worst case will be big O of log n. That's the worst case. What about the average case? The average case time complexity is in proportion to the expected number of swaps. I mean the swaps that are required to bubble down the new root element to its proper position, or say proper level. By new root, I mean the last node that you used to replace the original root. The random variable for this expected number can be the event when the new root element is being swapped at each level. So that's a constant number 1. Well, of course, it may or may not happen. If it happens, that's a number 1. If it doesn't, that's 0. When we discussed the insert method, we assumed that the probability of swapping at each level is 50%, because we have no way to know how big or small the newly inserted element is. So it's fair to assume the newly inserted element is random and arbitrary. So it has a fair chance to be either bigger or smaller than its parent at each level. However, that assumption is not applicable here when we are talking about the delete method. What we are dealing here is this. We moved one of the smallest elements from the leaf level to the root, and then gradually bubble it down. It's not a random element, and it's certainly smaller than elements at most, if not all levels. Based on that, we will do a rough estimate. I mean, an estimate that's probably rougher than what you have seen in the other videos of this series, but still acceptable. We will assume that the probability of swapping at most levels is 100%. Based on that, we can start computing the expected number of swaps. The way that you compute an expected number stays always the same. It's the sum of the set of items. Each item is the product of the random variable and its corresponding probability. When we plug in all the numbers, we will have this. Since both the random variable and the corresponding probability at each level are ones, we are essentially adding up a bunch of ones. And how many are there? The same as the height of the heap. As we learned in the past, if there are n nodes in total in a heap, then its height can be estimated as log n. So the expected number of swaps is in proportion to log n. The time complexity Tn is in proportion to this expected number of swaps, and it runs on big O of log n. That's the average case for the delete method. Now, we have covered the delete method of heaps and its time complexity of the best, worst, and average case. It's worth comparing the 3 different cases between the insert and the delete methods. The highlight should be the average case. The average case for the insert method runs on constant time, but for the delete method, it runs on big O of log n. Although you were given how things are computed and deduced mathematically, it's better to know why there's such a difference from a more intuitive approach. When a random value is inserted to a heap, it's most likely to be bubbled up for only a few levels, maybe 1 or 2 levels, and the number of that levels can be approximated to a constant number, because the randomness nature makes it increasingly less likely to be bubbled up at each level. Remember that you need to multiply all those 50% to calculate the probability of the newly inserted node to be bubbled up at the current level. When it comes to the delete method, the randomness assumption no longer stands. When you move one of the smallest elements to the root, it's most likely for it to be bubbled down to or near the leaf level again. Okay? That's why it takes log n swaps. As you know, log n here is the estimated height of the heap. In this video, we covered everything about the delete method of heaps, and its time complexity analysis of the best, worst, and average cases. In the next video, we will dive into the topic of heap sort.